Picture this. It's 1946, and a Russian immigrant working in a Chicago machine shop discovers that Detroit's beloved Flathead V8 has a fundamental design flaw that's destroying engines across America. He fixes it with a modification so simple, so elegant, that Ford's own engineers will spend the next 5 years trying to figure out how he did it. This is the story of how one man with a lathe and some Soviet engineering training embarrassed the entire American automotive industry. Chapter 1. The Flathead Problem. Detroit's Blind Spot. By 1946, Ford's Flathead V8 was dying, and everyone knew it except Ford. The engine that had powered everything from bootleggers to bombers was hitting a wall. Not a performance wall, mind you. A thermodynamic wall. A physics wall. The kind of wall you can't fix with bigger carburetors or hotter spark plugs. Here's the problem nobody at Ford wanted to talk about. The Flathead's combustion chambers were shaped like bathtubs. Upside-down bathtubs. The flame front had to travel sideways through these chambers, around the valve pockets, fighting its way through a maze of cast iron before it could do any useful work. It was thermodynamically insane. Picture trying to light a fire in a cave with multiple rooms. That's basically what was happening inside every Flathead cylinder. At low RPM, the Flathead was fine, docile even, smooth as butter at idle, but push it past 4,000 RPM and the whole thing became a heat pump. The exhaust valves would glow cherry red, literally red hot. You could see them glowing through the spark plug holes if you were stupid enough to look. The cylinder heads would crack. Not might crack, would crack. The valve seats would pound themselves into the block like they were trying to escape. And if you were really unlucky, the whole engine would detonate itself into modern art. Expensive, unrepairable modern art. The heat problem was catastrophic. Stock Flatheads ran exhaust valve temperatures north of 1,500 degrees Fahrenheit. At that temperature, cast iron starts to lose its structural integrity. The metal literally begins to fail at the molecular level. Hot rodders were replacing exhaust valves every few thousand miles because they'd erode away like chalk. Detroit knew about this. Of course they knew. Internal memos from 1945 show Ford engineers documenting heat-related failures at an alarming rate. Charts, graphs, failure analysis reports. The documentation was extensive and damning. But here's the kicker. They didn't care. The Flathead was cheap to build. Soldiers returning from the war knew how to fix them, and Ford had invested millions in tooling. Redesigning the engine would mean admitting the Flathead was fundamentally flawed, and Ford doesn't admit mistakes. Ever. So hot rodders were left to deal with it. They tried everything. Bigger cooling systems with radiators the size of barn doors. Exotic fuels that cost more than the cars they went into. Custom head gaskets made from materials that could survive re-entry. Copper gaskets, aluminum gaskets, gaskets made from compressed asbestos and prayers. Nothing worked. The Flathead's architecture was the problem, and you can't fix architecture with bolt-on parts. By mid-1946, the smart money was on junking the Flathead entirely and switching to overhead valve designs. Cadillac was working on one, Oldsmobile two, even Chrysler was developing their Hemi. The Flathead's days were numbered. Then a Russian immigrant in Chicago figured out something Detroit's entire engineering department had missed. Chapter 2. Enter Viktor Konstantinov, the Russian nobody. Viktor Konstantinov was nobody's idea of an automotive genius. Born in Moscow in 1908, educated at the Bauman Technical School, he'd spent the 1930s designing agricultural equipment for collective farms, tractors mostly, big, slow, ugly tractors that broke down constantly because Soviet manufacturing was about as reliable as Soviet promises. The kind of boring, utilitarian machinery that kept the Soviet Union fed but wouldn't win any engineering awards. Nobody writes songs about tractor designers. He escaped to America in 1943 through a convoluted route involving Turkey, Britain, and finally, New York. The details are murky because Viktor didn't like talking about how he got out. Most people who left the Soviet Union during the war had stories they preferred to forget. By 1946, he was working as a machinist at a small shop on Chicago's South Side, making parts for local hot rodders who couldn't afford proper speed equipment from the big California suppliers. Viktor was quiet, kept his head down, spoke English with an accent thick enough to cut with a knife. The kind of accent that made people assume he was stupid, which was their mistake, not his. The other machinists called him the Russian when they bothered to call him anything at all. He kept to himself, worked his lathe with obsessive precision that bordered on compulsive, and went home to a boarding house every night. No wife, no family, no social life, just work and more work. But Viktor had one advantage over every hot rodder in America. He'd been trained in Soviet engineering schools, where they didn't have the luxury of throwing horsepower at problems, or throwing money, or throwing anything really, because the Soviet Union was perpetually broke. Soviet engineers had to make things work with whatever materials they had, whatever design constraints they faced, whatever political commissar was breathing down their necks that week. They had to think differently. Efficiency wasn't a goal, it was survival. In the spring of 1946, a customer brought Viktor a cracked Flathead, the 8th one that month. The guy was trying to build a lakes racer and kept melting exhaust valves, kept destroying engines faster than he could afford to replace them. He was ready to give up, switch to an old straight 8, or maybe just sell the whole project and buy a Hudson. Viktor told him to leave the heads, give him 2 weeks. What Viktor did next would change hot rodding forever. But to understand why it worked, you need to understand what he saw that Detroit didn't. The Flathead's problem wasn't the combustion chamber shape. That was a symptom. The real problem was heat distribution. The exhaust ports ran through the block, right next to the cylinders. The hottest part of the engine, the exhaust system, was directly heating the coldest part, the intake charge. It was backwards, thermodynamically insane. And yet Detroit had been building them this way for over a decade without questioning it. Viktor didn't try to fix the combustion chambers. That would require new heads, new castings, new tooling, basically redesigning the entire engine from scratch. Instead, he looked at the cooling system. Specifically, the water jackets around the exhaust ports. The modification he developed was so simple that people initially thought it couldn't possibly work, but it did. And when word got out, hot rodders started making pilgrimages to a machine shop on Chicago's South Side to see the Russian who'd outsmarted Detroit. Chapter 3: The Secret Modification. Here's what Viktor did, and I want you to understand how ridiculously simple this was. He blocked off portions of the cooling jackets around the exhaust ports and redirected coolant flow to the intake side of the block. That's it. No new parts, no exotic materials, just strategic plugging of coolant passages with brass inserts. Think about that for a second. Detroit had hundreds of engineers with degrees from MIT and Purdue. They had testing facilities, dynamometers, millions in research budgets, and a Russian machinist with a lathe figured out something they'd missed. But here's where it gets clever. Viktor didn't just block the cooling randomly, he'd done the math. Soviet engineering training emphasized thermodynamics, heat transfer calculations, the kind of theory that American engineers often skipped in favor of just building stuff and seeing what happened. Viktor calculated the exact heat load on different parts of the block. He figured out where the hottest spots were, where the coolest spots were, and how coolant was flowing through the system. Then he strategically redirected flow to create a thermal gradient that actually helped the engine instead of fighting it. The exhaust ports ran hotter, much hotter. But that was okay because the exhaust gases were already hot. Letting that area run hotter meant less thermal stress, less expansion and contraction, fewer cracks. Meanwhile, the intake side ran cooler, which meant denser air charges, better volumetric efficiency, more power. The valve seats stopped pounding out because the thermal cycling was reduced. The head stopped cracking because the temperature differentials were smaller, and the engine could rev higher because the intake charge wasn't being preheated by the exhaust ports. Viktor's first modified engine made 160 horsepower at 5,000 RPM. A stock Flathead made 100 at 4,000, And it did this for hours without overheating, without detonation, without any of the failures that had plagued flatheads for years. The customer who'd brought in the cracked heads took his lakes racer to the Bonneville Salt Flats in August 1946. He ran 138 miles per hour in a car with a stock displacement flathead, using pump gas. The racing community lost its collective mind. Chapter 4. The technical genius behind it. To really appreciate what Viktor did, you need to understand heat transfer in internal combustion engines. And I promise this won't be boring because what Viktor figured out was actually brilliant. In a conventional engine, you want even cooling. Hot spots cause detonation. Cold spots cause incomplete combustion. Detroit's approach was to cool everything equally, which sounds logical until you realize that different parts of the engine have wildly different heat loads. The Flathead's exhaust ports were buried in the block, surrounded by water jackets trying desperately to cool them. But exhaust gases can exceed 2,000 degrees Fahrenheit. You're not going to cool that effectively with water jackets. All you're doing is heating the coolant, which then heats everything else. Viktor's insight was to let the exhaust ports run hot. Stop trying to cool them. Instead, use that heat to maintain consistent metal temperatures in the exhaust path. This reduced thermal stress and actually improved exhaust flow because the gases stayed hot and expanded. Meanwhile, redirect all that cooling capacity to the intake side. The intake ports needed to be cold. Cold air is dense air. Dense air makes power. By keeping the intake passages cold, Viktor was effectively giving the engine a supercharger's worth of additional air density without any mechanical complexity. The math is actually pretty simple. For every 10 degrees Celsius you cool the intake charge, you get roughly 3% more air density. Viktor's modification cooled the intake side by approximately 30 degrees compared to stock. That's nearly 10% more air, which translates directly to power. But the brilliance went deeper. The stock Flathead had massive temperature gradients across the block. The exhaust side would be 200 degrees hotter than the intake side. This caused the block to warp, head gaskets to fail, and thermal stress to crack everything. Viktor's modification evened out the temperature distribution, not by making everything the same temperature, but by creating deliberate, consistent gradients that the block could handle. The exhaust side ran hot, the intake side ran cold, but the transition between them was smooth and predictable. He also did something that wouldn't become standard practice for another 20 years. He insulated the exhaust ports from the rest of the block, not with fancy ceramic coatings or exotic materials, just with air gaps created by his blocked-off cooling passages. Air is an excellent insulator, and by trapping air around the exhaust ports, he was creating thermal barriers that kept exhaust heat where it belonged. The valve seat recession problem, which plagued every high-performance flathead, disappeared almost entirely. Valve seats fail when they heat up and cool down repeatedly, expanding and contracting until they pound loose. By maintaining consistent exhaust port temperatures, Viktor eliminated most of that thermal cycling. Quality control was obsessive. Every cooling passage modification was measured to within 0.005 of an inch. The brass plugs had to be precisely sized and located. Too much restriction, and the engine would overheat. Too little, and you'd lose the thermal gradient benefits. Viktor spent weeks testing different configurations on a borrowed dynamometer before he was satisfied. The result was an engine that made more power, ran cooler under load, lasted longer, and used less fuel than a stock Flathead, all from redirecting coolant flow. No new parts, no exotic materials, just thinking about the problem differently than Detroit had. Chapter 5. Testing and Results. That shocked everyone, word spread fast in the hot rodding community. By late 1946, Viktor had a waiting list of customers wanting the modification. He called it the thermal optimization process, which was very Soviet and very boring. Hot rodders called it the Russian hack, which was catchier. The dyno results were incredible. A modified 239 cubic inch flathead consistently made 160 to 170 horsepower. Stock engines made 100. That's a 60 to 70% power increase from what was essentially a cooling system modification. But the real shock came at the dry lakes. Muroc, El Mirage, Bonneville. Racers with Viktor's modification were suddenly running 10 to 15 miles per hour faster than identical cars with stock cooling. More importantly, they were finishing races. Stock flatheads would overheat, detonate, or blow head gaskets. The modified engines just kept running. In October 1946, a roadster with a Viktor-modified flathead set a new class record at Muroc Dry Lake, 142.7 miles per hour. The previous record had been 128. The difference was entirely the cooling modification. Reliability testing was even more impressive. One customer ran his modified flathead for 73 consecutive hours at 4,500 RPM on a dynamometer. Oil temperature stabilized at 220 degrees, coolant temperature at 190. The engine never varied more than 2 degrees from those numbers. A stock flathead would have grenaded itself within an hour at that RPM. The fuel economy. Improvement surprised everyone, including Viktor. Because the intake charge was denser and cooler, combustion efficiency improved. Modified engines used about 15% less fuel for the same power output. This wasn't why people were doing the modification, but it was a nice bonus. Temperature measurements told the real story. Stock flatheads showed exhaust port temperatures of 550 degrees Fahrenheit and intake port temperatures of 300. Viktor's modification ran exhaust ports at 625 and intake ports at 210. The exhaust ran hotter, the intake ran colder, and somehow the whole engine was happier. By early 1947, Viktor was modifying 5 to 10 engines per month. He could have done more, but he was meticulous. Every engine got custom calculations, custom plug placement, custom testing. He wasn't running a production operation. He was crafting individual solutions. The price was steep. $75 per engine in 1947 money. That's over $1,000 today just for labor. Plus, you had to provide your own heads and block. But for racers who were tired of replacing engines every few months, it was a bargain. Chapter 6. Detroit's Response: Denial and Theft. Ford heard about Viktor's modification in early 1947. Internal memos show they initially dismissed it as backyard tinkering that couldn't possibly improve on factory engineering. After all, Ford had designed the Flathead. What could some Russian machinist know that they didn't? Then in April 1947, Ford quietly purchased a Viktor-modified Flathead through an intermediary. They took it back to Dearborn, tore it down, measured everything, tested it on their dynamometers. The results matched what hot rodders had been reporting. More power, better reliability, improved fuel economy. Ford's response was predictably corporate. First, they tried to hire Viktor, offered him a job in their engineering department with a nice salary and benefits. Viktor said no. He liked working for himself, liked the freedom to experiment. Plus, he didn't trust large corporations, especially American ones. Second, Ford's legal department looked into whether they could sue Viktor for modifying their engines. Turns out you can't sue someone for making your product better. There was no patent infringement, no trademark violation, nothing illegal about blocking off coolant passages. Third, and this is where it gets interesting, Ford started incorporating Viktor's ideas into their own development. The 1949 Ford overhead valve V8 showed evidence of thermal management strategies that looked suspiciously similar to Viktor's work. Separate cooling zones for intake and exhaust, thermal barriers around exhaust ports, deliberate temperature gradients instead of uniform cooling. Ford never admitted where these ideas came from. In fact, their patent applications for the new engine carefully avoided mentioning anything that might acknowledge Viktor's prior work. This was standard Detroit practice. Take ideas from the aftermarket, claim them as your own, act like you invented them. General Motors and Chrysler were watching too. GM engineers visited Viktor's shop in late 1947, asking questions, taking notes. Viktor showed them everything. He wasn't proprietary about his work. He figured knowledge should be shared. Very Soviet of him. Chrysler sent a more official delegation, offered to license Viktor's cooling modification for their industrial engines. Viktor said no again. He didn't want his work ending up in tractors or generators. He wanted it in race cars, in hot rods, in machines that push boundaries. By 1948, every major automotive engineering journal had published articles about selective cooling, thermal management, and optimized temperature gradients. None of them mentioned Viktor by name. The credits went to Detroit engineers who'd independently developed these concepts. But the hot rodding community knew the truth. Every serious flathead builder incorporated some version of Viktor's modification. The exact plug placement became trade secrets, with each shop developing their own variations. But the principle, cooling the intake and letting the exhaust run hot, that came from one Russian machinist in Chicago. Chapter 7. The Underground Spread. Viktor's modification spread through the hot rotting underground like wildfire. But here's what's fascinating. It spread as knowledge, not as a product. Viktor never mass-produced anything. He modified engines individually, but more importantly, he taught others how to do it. By 1948, machine shops across California, Texas, Michigan, and the Midwest were offering thermal optimization services. Most of them had learned the technique from someone who'd learned it from someone who'd visited Viktor's shop. It was like a folk tradition, passed down through demonstration and practice. The modification evolved as it spread. Some builders used different plug materials. Others experimented with partial restriction instead of complete blocking. A few tried to improve on Viktor's math with their own calculations. Most of these variations didn't work as well as the original, but some found valid improvements. By 1950, you could find Viktor-style cooling modifications on everything from street rods to midget racers to early dragsters. The modification had become standard practice, part of the hot rodding knowledge base. Nobody called it the Russian hack anymore. It was just how you built a flathead if you wanted it to live. Viktor himself had moved on to other projects by then. He developed a reputation as the guy who could solve impossible problems. People brought him engines that nobody else could fix. He'd study them, run calculations, machine custom parts, and somehow make them work. What's remarkable is how little credit he got. Hot Rod magazine ran an article about advanced flathead cooling in 1951, mentioned the technique, showed the modifications, explained the theory, never mentioned Viktor's name. When readers wrote asking who'd developed this, the magazine responded vaguely about multiple sources in the hot rodding community. This bothered some people who knew the real story, but Viktor didn't care. He wasn't in it for fame or recognition. He just liked solving problems, making engines work better, pushing boundaries. Very Soviet mindset for someone living in capitalist America. Chapter 8. Why it worked so brilliantly. The reason Viktor's modification works so well comes down to understanding what an engine really is. It's not a power producer. It's a heat pump that occasionally makes some useful work on the side. Most of the energy in gasoline becomes heat, not motion. Managing that heat is the key to everything. Detroit's approach was to cool everything equally because that's simpler to engineer and manufacture. Uniform cooling means uniform tooling, standardized water jackets, no special cases to account for. But uniform cooling fights against the engine's natural thermal characteristics. Viktor's approach acknowledged reality. The exhaust side is always going to be hotter than the intake side. Instead of fighting this, work with it. Create deliberate temperature zones that optimize each part of the engine for its specific function. The exhaust needs to be hot for proper flow and to reduce thermal stress from cycling. The intake needs to be cold for air density and power. By embracing this dichotomy instead of fighting it, Viktor unlocked performance that Detroit's uniform cooling approach couldn't achieve. The modification also reduced the engine's biggest enemy, thermal stress. Metal expands when heated, contracts when cooled. Rapid changes in temperature cause fatigue and cracking. Viktor's modification created consistent, predictable temperatures that the metal could adapt to. Less cycling meant longer life. There's also the psychological aspect. Viktor wasn't constrained by, "that's how we've always done it" thinking. He didn't have decades of Detroit engineering dogma telling him what was possible and what wasn't. He just looked at the problem, did the math, and implemented a solution. Sometimes being an outsider is an advantage. Chapter 9. The Soviet Connection Nobody Talks About. Here's something that didn't come out until much later. Viktor's thermal management approach wasn't entirely original. He'd adapted it from Soviet aircraft engine design. In the 1930s, Soviet engineers were developing high-altitude engines that had to deal with extreme temperature variations. They'd figured out selective cooling as a way to manage thermal loads in aircraft engines. Viktor had worked adjacent to this program during his time in Moscow. He'd seen the principles, understood the math. When he encountered the Flathead's cooling problems, he realized the same concepts could apply. It was technology transfer from Soviet aerospace to American hot rodding. You can't make this stuff up. The Soviets were actually quite advanced in thermal management because they had to be. Their materials weren't as good as American materials, so they had to be smarter about design. They couldn't just throw better alloys at problems. They had to optimize the systems themselves. This is the irony. During the Cold War, while America was panicking about Soviet technical superiority, Soviet engineering principles were literally making American hot rods faster. One Russian immigrant with knowledge of Soviet aircraft design was improving American engines in ways Detroit couldn't manage. Nobody talked about this at the time, obviously. Viktor kept the Soviet connection quiet, and nobody asked too many questions. But years later, after Viktor had passed away, some of his notes were discovered. They referenced Soviet technical papers, thermal management research from Moscow institutes, calculations in Russian. Chapter 10. The Legacy and What Detroit Learned. Viktor Konstantinov died in 1978 at age 70. His obituary in the Chicago Tribune identified him as a retired machinist. Nothing about revolutionizing engine cooling. Nothing about outsmarting Detroit. Just another immigrant who'd worked hard and died quietly. But his legacy lived on in every engine that used selective cooling, thermal barriers, or deliberate temperature gradients, which by the 1980s was basically every high-performance engine made. Modern engines use principles that Viktor pioneered: separate cooling circuits for the head and block, thermal barriers around exhaust ports, strategic coolant flow to optimize intake temperatures. These are standard practices now, found in everything from economy cars to Formula One engines. Detroit eventually learned the lesson, though they'd never admit where they learned it from. The overhead valve engines that replaced the Flathead incorporated thermal management from the start. Not as crude as Viktor's blocked-off passages, but the same principles: hot exhaust side, cold intake side, thermal barriers between them. Computer modeling and CFD analysis now do what Viktor did with a slide rule and intuition. Modern engineers can simulate coolant flow, calculate heat transfer, optimize thermal gradients. But the fundamental insight that different parts of an engine need different cooling strategies that came from a Russian machinist in 1946. Chapter 11. Conclusion. The lesson. Detroit refused to learn. The story of Viktor Konstantinov is really a story about institutional blindness. Ford had the resources, the engineers, the facilities to discover what Viktor discovered. They didn't because they weren't looking. They decided the Flathead's architecture was the problem, so they focused on designing a replacement instead of optimizing what they had. Viktor wasn't smarter than Ford's engineers. He just asked different questions. Instead of, how do we replace the Flathead? He asked, why does the Flathead fail? And can we fix it without replacing it? Different question, different answer. This pattern repeats throughout automotive history. The outsider with fresh perspective solves problems that insiders think are unsolvable. The aftermarket innovates while the factories calcify. The immigrant with nothing to lose embarrasses corporations with everything to protect. What if Ford had hired Viktor in 1947? What if they'd embraced his modification instead of ignoring it? They could have extended the Flathead's competitive life by years. They could have owned the performance market instead of ceding it to Oldsmobile and Cadillac. They could have learned from someone who thought differently, but that's not how corporations work. They don't like being shown up by outsiders. They don't embrace ideas that come from machine shops instead of engineering departments. They'd rather pretend the idea was theirs all along, or ignore it entirely. Viktor's story reminds us that innovation comes from unexpected places. Sometimes it comes from Soviet-trained engineers working in Chicago machine shops. Sometimes it comes from people who aren't constrained by how things have always been done. Sometimes the best ideas are also the simplest, hiding in plain sight until someone bothers to look. The Russian who outsmarted Detroit didn't do it with exotic materials or complex designs. He did it with brass plugs and a slide rule. He did it by thinking about heat differently than anyone at Ford had bothered to think about it. He did it because he wasn't afraid to challenge assumptions that everyone else took for granted. Every time a modern engine uses selective cooling, every time thermal barriers improve efficiency, every time engineers optimize temperature gradients, Viktor's ghost is there, unnamed, uncredited, but present in every equation and every design decision. That's the real legacy. Not fame or fortune or recognition, just the quiet satisfaction of solving a problem that needed solving, of making engines work better, of proving that good ideas can come from anywhere if you're willing to listen. Detroit never really learned this lesson. They still miss innovations from the aftermarket. They still ignore ideas that come from outside their walls. They still think bigger budgets and more engineers guarantee better results. But every once in a while, a Russian machinist with a lathe proves them wrong, and the world is better for it.